going to finish up this chapter that we're on about current and resistance. We are going to do a couple homework problems, and that's pretty much it. You do have homework due tomorrow, and you do have a quiz over the weekend. Any questions before we get started? No. Okay. I remember what I was talking about last Tuesday, which is pretty miraculous, and also means that we're going to have a very short review on different temperature scales. What's your favorite temperature scale? Favorite temperature scale? That is a mistake. Kelvin. Kelvin is a great temperature scale. That's my favorite personally. Kelvin. Kelvin. K. Just Kelvin. Where 0 Kelvin actually means that there is zero heat in the system. Zero heat in system. Theoretically impossible to get to in the lab. And it's a safe set of units, because no matter what you're doing, if you do the calculations in Kelvin, you'll be okay. So very safe. What's the next one? Celsius. Celsius is a good one. Based on the 0 degrees is when water freezes. Water freezes to 100 degrees, water boils. Good standard. How do you convert between Celsius and Kelvin? Okay, a little bit louder. All right, so if you have 0 degrees Celsius and you add 273 Kelvin, you're at 273 Kelvin. So to convert between Celsius and Kelvin, you just add 273. Now, let me ask you, if I took the difference between two temperatures, so I had like T2 minus T1, and I wanted to make sure I got the right answer, would it matter if I were in Celsius or Kelvin? No, right? Because if I do it, no matter which one I do it, 1 degree, if you change 1 degree Celsius, that's the same as changing 1 Kelvin. You know, it'd just be like going back and forth between 0 degrees Celsius and 10 degrees Celsius and 273K and 283K. The difference will be the same. So Kelvin and Celsius, great. If you ever run into something in Fahrenheit, you look up how to convert it to Celsius or Kelvin, which I think you like multiply it by 9/5 and subtract, add 32. Yeah, but Celsius or Kelvin, stick to those two. Given that, a good problem to start out with in this chapter would be number 14, where, if you recall, what we were doing right before we stopped yesterday was we were looking at the temperature dependence of the resistivity of a substance. Okay, so we talked about, okay, what would make something resist current. And we talked about, well, it would be atomic or molecular. I didn't have this word on Tuesday either, but the shape of the molecules. Structure is the word. Atomic or molecular structure. And that'll tell you how easily it'll be for electrons to flow through the material. But we also came up with the idea that if something is warmer, all the stuff that the object is made up of will be moving around, and that will make it more difficult for our electrons to be able to flow through it. So the idea is higher temperature means higher resistance. And that led us to this equation, where this rho is the resistivity of any substance. And we expect the resistivity to increase as the temperature increases. So like this would be the temperature at, like apparently for this. Apparently for this problem, they're setting the like room temperature, and there must be a typo here. They set it to 283 C. And can someone tell me why this is wrong? That is very warm. That does not make sense. Also, they should absolutely have like a degrees here if they want to talk about Celsius. And really quick, if they had put a K here, would that have been better? Like 283 Kelvin, is that a reasonable temperature? Yeah, it is, right? Because 283 Kelvin, that's like 10 degrees Celsius. So you're like 10 degrees above freezing, which is chilly, but like not ridiculous. But they have a C in this problem, so who am I to tell them that they're wrong? Okay, T naught, 283 C. Okay, so yeah, rho naught would be like the base temperature. So at this base temperature of 283 degrees Celsius, the base resistivity of this would be 10.5 times 10 to the negative fifth ohms times meters. So for every, okay, ohms times meters. Now, we're also given this alpha. And so basically this alpha is a coefficient that tells you how much your resistivity is going to increase per unit degree, like per unit Celsius. So alpha of this, whatever this substance is, 9.5 times 10 to the negative 3 inverse degrees Celsius. That's a 3 up there. So for every degree Celsius you increase, your resistivity increases by 9.5 times 10 to the negative third. A factor of 9.5 times 10 to the negative third. Sorry, that said right. Okay. Everyone kind of happy? Well then, let us run through this problem. Where they want an equation for some temperature T2 where the resistance of the wire will be twice as high. So that means if the resistance of the wire will be twice as high, that means the resistivity will be twice as high. So we'll have like a rho 2 that is twice the rho naught. Sound okay? So we're looking for T2, and we need to be the temperature at which rho 2 is twice rho naught. And for this one, what I would do is I would say, well, rho 2 will be rho naught plus rho naught alpha, T2 minus T naught. And I need that to equal twice the base resistivity. Everyone pretty happy? And then we're just going to take this and we're going to solve for T2. So I'll subtract a rho naught from both sides. So I'll have rho naught equals rho naught alpha. T, that's an alpha. T2 minus T naught. Looks good. Alpha. What's going to happen to my rho naught here? Yeah, I can, oops, I didn't mean to erase it. I can cancel it. And then again, I'm just solving for T2, so I will divide both sides by alpha. And I will add T naught to both sides. So I have T naught plus 1 over alpha. And that's what they want to see for part A. So far, so good. Okay. For part B, they just want you to plug in numbers to this. So for B, you'd say, well, T2 equals T naught 83 degrees Celsius plus 1 over 9.5 times 10 to the negative third 1 over degrees Celsius. Do we expect something larger or smaller than 283? So if 283 is our base and our resistivity is larger at T2, do we expect T2 to be more or less than T naught? As temperature increases, does resistance increase or decrease? Increased, right? So if I've said resistivity has increased, then you probably should be telling me that temperature has increased. Okay, so I expect T2 to be more than T naught. And if you run through this, you do get that T2 is more than T naught. Okay, is that real good? Okay, well then I got to tell you, part C is where I always make a obvious mistake. And I'm gonna circle around part C because I haven't actually derived something for part C. But part C tells you if a wire is 1 meter long and it's got a radius of 1 centimeter, what would its resistance at 2 T naught be? Okay, and I want to come back to this because we haven't actually derived this equation. But for 2 T naught, could you just plug in 288 degrees Celsius? Yes. Well, I'm saying like absolutely not, right? Yeah, because that's T2. That is not twice 283. And maybe I'm the only one who ever made this mistake, but I spent a lot of time trying to shove that 288 degrees Celsius into my equations. 2 T naught means that you've doubled the initial base temperature. That does not mean that your resistivity has doubled, right? Because all you have to do is increase it by 5 degrees Celsius and your resistivity is doubled. So this, at 2T naught, we would expect a very, very high resistivity. Sound okay? Okay, let's put that problem on hold while we talk about the difference between resistance and resistivity. Okay, so we have this idea of resistivity rho, which is basically tied to whatever type of material you have. Like, do you have copper? Do you have rubber? Rubber would have a high resistivity, while copper would have a low resistivity. Sound okay? And the resistivity will be true of all copper. Well, no matter what piece of copper you pick up, it'll have the same resistivity. Now, this is as opposed to resistance, where resistance is tied to some object. So like, while this is made of cardboard and it will have some resistivity, which is the same as all over cardboard, it will have a very specific resistance. Makes sense? Which will be different from this piece of cardboard. Excellent, excellent. Okay, so the equations we have that involve resistance right now, Ohm's law, V equals IR. So we have this idea that resistance kind of mediates how much current a certain voltage can have. But I would like, of course, to be able to build a resistor and know what its resistance ought to be before I hook it up to a battery. So I don't just want to be building resistors and having to like hook it up to battery to figure out how much resistance it has. I would like to be able to just say, here are the specs for my resistor, build it. What sort of things would you need to know? Like, what sort of specification would you give someone to say, this is the type of resistor I want? Okay, go home and build me a resistor. What questions do you need to ask me right now? Say again? I'm really sorry. Oh, okay. I need a resistor that is 10 ohms. I need a 10 ohm resistor. You get home, you're trying to build a resistor. What questions do you need answered? If there are no questions that need to, okay, like, how are you going to do this? You're at your house. You need 10 ohms. What are you going to do? Run a current through something. What sort of things might you run a current through? Okay, maybe a copper wire. If the copper wire is too low of resistance, what will you go to next? 2 copper wires. I like it. More copper. No one's going to try like a ceramic plate? Maybe. Where you might start thinking about like what you need to build your resistor out of. Yeah, so you need a material. You might think about ceramics. Ceramics are pretty weird. So yeah, so one thing that's going to go into this equation, what sort of material do you think you should use? And that makes sense, right? Because you have different materials have different resistivity. So a copper wire would give you a much different resistance than a ceramic of the same dimensions. And while I'm talking about dimensions, the next thing you should be asking me is how big should it be? And we model all resistors like wires, like cylinders, where you're going to specify the length of the thing and the cross-sectional area. Okay. If I want a higher resistance, should I make a shorter cylinder or a longer cylinder? So I want more resistance. Do I want to increase the length or decrease the length? Increase. I like that. Where the way you might want to think about this is you might want to think about resistance. So the resistance is just like a bulk. Like if I need to get from where I am to the other side of the room, the resistance is the amount of work I've got to do to get there. If this room is twice as long, I've got to do twice as much work. Okay. What about the cross-sectional area? If I want more resistance, do I want a bigger area or a smaller area? Smaller area. Absolutely right. Where, again, I'm trying to get to that door, and pretend for a second there's a bunch of people in this room. If I had to double the area to go through, I'd have more pathways to get to that door. But if we're all just scrunched up into one pathway, then it's going to be very difficult for anyone to get anywhere because we're all trying to occupy the same space. Okay, excellent. And so this is where we end up with the total resistance of some object is equal to its resistivity multiplied by its length and divided by its cross-sectional area. And so this is where resistivity is getting its units of ohms times meters, because I have length in meters, area in meters squared. So I'm going to cancel that out, and I'm going to be left with 1 over meters from that. And so if I multiply that by an ohms times meters, I can get that last meter to cancel out and be left with ohms, which is what I want to have. Okay. Now, let's take this and let's run back to right here, where if I want to figure out the resistance of this thing, R will equal the resistivity at 2T naught multiplied by this thing's length, which we use capital L for, and divided by its area. Now we were given the length right here, length, but we weren't given the area, we were given the radius. How would we find the area if we had the radius? Pi r squared. We would say A equals pi r squared. And that you can pretty much assume that's going to be true for all of these resistors, all of these wires, everything that we're using here. You can assume that they're cylinders unless something specifically says that they're not. There'll occasionally be a problem, and we'll do one right after this where that's not true, but they have to say it. It's not assumed. Okay. Do you guys want to run through? Well, I guess there's not much to run through. You just plug everything in. Do be careful to change your centimeters to meters. So it'll mess you up otherwise. But otherwise, just plug everything in and you'll be good. Okay, everyone pretty happy? Excellent. Then there's one problem here that I actually really like. I would like to do, there it is. I want to do number 5. Where number 5 says that we have a battery and we are going to hook it up to a resistor, and then we're going to hook it up to a rectangular object where this rectangular object can be hooked up one of several ways. It can be hooked up like this, where the width is A, the length is C, and the height is B. Or we can hook it up same object and everything, just different orientation, like so. Or we can hook up a third way. Perspective, like that. Okay, for all of these, we have the same battery, this extra resistor, the same resistor. I think they just added that because they wanted to make sure that you're not short-circuiting anything. And this is the same object. We're just rotating it into different orientations. Does that make sense? Did I draw that clearly enough? Okay. So what we're trying to figure out is which one of these situations is going to have the greatest current and which one's going to have the least current. So we're ranking the currents across here, where V equals IR. And so basically the situation where this block is going to give us the highest resistance is going to have the lowest current. So we're really ranking the resistance of each of these shapes in their different orientations. Sound okay? Okay, let me just call this A, B, and C. Okay, which one do you think is going to have the highest current and therefore the lowest resistance? A, you're absolutely right. Because for A, it's got the shortest length to travel through, right? So it's going from the thin sides, and it's got the biggest cross-sectional area to travel through. So this is going to have the highest current over there. Biggest L, smallest, biggest L, and also the biggest A. Okay. Which one's going to have the least amount of current? So the biggest resistance and the lowest current. C, I like C, because that's the one where the current has the longest path to get through, right? So that's the, oh, there, I'm sure all of you were, this has the smallest L. This has the largest L. Perfect. Largest L. It's actually got the smallest A. Okay, and then of course we have in the center here, we got B, where it's got a B's worth of length to get through, which is more than A but less than C. And its cross-sectional area is somewhere between A and C as well. Does that make sense? Okay, cool. Same, and basically I wanted you guys to see it's the same object, and just the geometry of how you approach it is going to change the way its resistance is. Okay. Okay. Everyone good here? Yeah, so this one we're ranking the resistance from lowest to highest, and therefore the current from highest to lowest. I've got one more of these resistance problems that might be good. Do you guys want to do it, or do you guys feel very confident? Shall we do it? Okay. Give me a second. Let me. Yeah, it's this one. Number 12. So number 12 is nice because we get to talk about gauges. So we have a 2-gauge copper wire. Copper wire that is 3.75 meters long. Okay, and we're going to figure out its resistance. We're going to figure out its resistance. So that'll be in ohms. Okay. I want to draw a picture of this clearly, right? What when I draw a picture of this, what shape will the wire be in? And what I'm asking is, should I draw a wire like a rectangle, or should I choose a different shape? A nice cylinder, maybe? Let's just be clear, because I'm not sure I'm saying it right. I want a cylinder. Okay, I'm sure you were probably thought that was obvious, but I want to make it obvious because what that tells you is that the cross-sectional area is always going to be the cross-section of a circle. Okay, so whenever you're thinking of the area, always be thinking pi r squared. Okay, this looks really good. But we need, if we want the resistance, we're going to need to figure out that area, so that pi r squared there. And the way you do it is through a gauge. Have you guys used gauges before? Okay, and then that's what you should do. So like a 4-gauge, you said? Yeah, 4 gauges are big because gauges work inversely. So like the bigger the gauge, the smaller the wire. Makes sense. So like when you're like doing the pure series things, you started a high gauge and you work towards smaller gauges. Maybe. Okay, you do. Where a 2-gauge, what we have is a 2-gauge has a diameter of 6.54 millimeters. And just so you know, gauges are actually like a standardized unit. So that's just like you can say millimeters, you can say gauges, and you know you have to do the conversion, but it's a standardized unit. Okay, I got my 2-gauge, so I know the diameter. How am I going to relate that to radius? Half of the diameter, so I could just say like this is d over 2 squared like that. Okay, I have the length. How do I find the resistivity? Now let me tell you, if you saw the problem in front of you, you'd be like, obviously. But you would Google the resistivity of copper, right? Like if someone doesn't give you the chart, which this problem does, but we know it's copper. All copper has the same resistivity, so you just Google resistivity of copper. Sound okay? Okay. Okay, and then you just plug in your numbers. So like the resistivity of copper that they give us is 1.68 times 10 to the negative 8 ohms meters. We have a length of 3.75 meters. And when we plug in our numbers here, one, we're going to change this millimeters to meters. That's 0.00654 meters squared. And two, we're not going to forget to square the 2 on the bottom there, and that's going to become a 4. And so we'll get with 0.0019 ohms. This is a small resistance. Is that reasonable? What do you think? Because I have nearly 4 meters of this stuff. Would 0.002 ohms, does that seem like a reasonable resistance? Okay. It should be, because it's copper. And copper should have low resistances, right? That's what we use for wires in all of our walls, copper. So it's very reasonable that our resistance is low. However, I want you to think about this for the next couple of weeks, 4 weeks, 5 weeks. This 3.75 meters, so that it's about 4 meters. Think for a second about how much wiring has to go into your house. Like, how much wiring went into this room where we have outlets and lights and whatever power source that they're pulling this from, they're having to wire from that power source out to each of these things. So they definitely have wires that are longer than 4 meters. Okay? And if for every 4 meters we get 0.002 ohms of resistance, that's going to build up kind of quickly. So we will talk about how to deal with this when we start talking about AC circuits. But just be aware that there is an issue here. Sound good? Okay, cool. Well then, I want to talk about, I've got a few more things. The last thing with resistance I want to discuss is superconductors. Because in less than 5 weeks, I'm going to see if I can get a superconductor and we can do cool, fun stuff with it. Where superconductors, there's different types of superconductors. There's ceramic superconductors and metallic superconductors, where the metallic are type 1. Type 1, these tend to be metals. And you need to cool them down to liquid helium temperatures, which is about 4K. Note that 0K is absolute zero and theoretically impossible to get to. So when we're saying 4K, that's very cold. Okay, that's very, very cold. Type 1. Type 2 tend to be ceramics and crystals. Sometimes people call them new because they were discovered in the 80s versus like the early 1900s. Not early, mid 1900s, 1950s, I guess. These, you only need liquid nitrogen to cool down, and that's around 77K. They call these room temperature superconductors occasionally. 77K is nowhere near room temperature, just so you know. But since it's so much more than 4K, you basically, for liquid helium, you need to have a specific lab set up with a room for liquid helium, because it will not only freeze people very quickly, it will outgas so quickly you'll suffocate. Liquid nitrogen is a little more reasonable. So you can play with liquid nitrogen at room temperature and no one dies. It's very nice. But the idea behind superconductors, and there are a lot of ideas, So let me constrain ourselves to type 1, because those were discovered first, and the theories apply to type 1, and type 2s theories are in process. But the idea behind this is you have your metal and you cool it down. And now temperature decreases so resistance decreases when temperature goes down. And things also start settling out. So like they stop moving around, they get very still, very, very calm. And what will happen once you hit that a superconducting limit is your electrons will start to pair up. They'll just cool down enough until they condense into little electron pairs. And the weird thing about this is there's quantum mechanical effects, but what it allows is for these electron pairs to pass through each other. And so our initial understanding of where resistance comes from, where you're like doing the pinball machine and the different objects are getting in each other's way, that doesn't apply anymore. The electrons just pass through each other. They're like ghosts. And in that way, the resistance of a material goes to 0. And not like practically 0, it goes to 0. Because the mechanism for resistance no longer applies. And so we will talk about applications of this when we get to magnetism. But it is like a really weird system, because it's not one of those like friction is negligible or it gets really small. It is absolutely 0. And 2, with resistance being 0, there's no limit on how much current you can generate. You can just speed those electron pairs up to as fast as you need them, because they'll just keep going forever. There's nothing slowing them down or stopping them. Sound okay? Okay, keep that in your head for like 2 weeks, and things will get really cool after that. Just so you know, type 2, there's no accepted perfect theory for this. They basically think it should be kind of like BCS theory, but they haven't shown it to be true, especially at the higher temperature. The math doesn't quite work. And so they kind of pull in a couple different theories and say it's close enough, and it probably is. But there's not one solid perfect theory. And oddly enough, a lot of the superconducting wire that we use is actually type 1. So anytime you see like a superconducting magnet, like in giant particle accelerators, they're actually using liquid helium to cool that down, which is stunning. Oh, you know what? I learned that like a decade ago, and it still stuns me, which is why I just said it. I'm constantly shocked by that. Liquid helium is hard. Okay, anyway, moving on. The last thing in this chapter is power, which you probably saw in mechanics, but it wasn't that exciting. But now it's going to be exciting. If you remember, power was the rate at which work got done. So, and if you remember, work was change in energy. So if you had like energy over here and you needed to move it over there, work was how much energy you moved, and power was how quickly you could do that. So power was just change in energy over change in time. Sound okay? Now, in mechanics, this might not have been that interesting because we only had a really small different types of power that we could talk about. But now that we've added an entire dimension of electricity, we have more types of energy to talk about. So, for example, we could talk about how quickly electricity gets pumped into the lights, which are off, my overhead, which is on, and how that gets converted into light, which also has energy. We also can think about your electronic device, an electric car. An electric car is a good one, where there's electrical power, and when you turn on your car, that gets converted into kinetic energy. So you have electrical energy, and it gets converted to kinetic energy, and how quickly that happens is power. How this is going to look math-wise is, so we have power equals change in energy over change in time. You can definitely think about this in terms of like a derivative, where that's just change in energy over change in time still. For electrical energy, so we want to think about electrical energy right now, which we derived last week when we were doing capacitors, if you remember. And we had a bunch of different, this was the one where we had a whole bunch of different equations. But one of the equations we had for energy was Q delta V. So just, and it looked like this. It was, I want to take a charge and I want to move it through some potential difference. And that would take some amount of energy to do that. Okay, a nice way to look at this when I want to think about current. So before I was taking a charge and I was moving it through some potential difference. But now I'm talking about current. I want to think about, I'm taking this current, I'm going to run it through some potential difference. And that current is made up of these charges. So I want to say, well, I'm really doing like a dq dt, where a derivative of charge with respect to time, that is current. That's just like the basic definition of current there. So that means power is some current moving through some potential difference. And just like we had a lot of ways to talk about energy, we're going to want to talk about this in a few different ways. Basically, by looking at Ohm's law, where if V equals IR, then you could write this as current times resistance. So I squared R. You could also say, well, if V equals IR, I equals V over R. And so this is V over R times V. And so you have V squared over R. Okay, so we have these three equations for power. We have V squared over R, we have I squared times R, and we have IV. And generally, you know, you use the one that makes sense for the problem. But even more than that, let's say I have my light bulb right here, like this. I have current going through here, like that. And this light bulb is giving off light. So the power that this battery is putting into the circuit, and not only power, but it's putting in energy per unit time. So like every second it puts in X amount of energy. And so the power it's putting in, I'm saying it's putting in some amount of energy per unit time there. And that will equal the power out of the circuit in the form of light. And so you could very easily measure how much energy is coming out of that light bulb. And the amount of energy coming out of that light bulb every second is going to equal the amount of energy going in from that battery every second. Excellent. Now, things to think about. For this light bulb, generally when you think about the power coming out of that light bulb, you think about an I squared R. not that you can't do like a V squared over R or anything like that, but an I squared R, what that resistor is doing is literally when electrons move through it in a current, it's sucking up some of that kinetic energy and transforming it into light. And so that's why a lot of times you think about the power going through the resistor in terms of the current going through the resistor, because the current is what's where the energy is being exchanged. And this is opposed to the battery, where a lot of times you think about batteries, you want to think about both current and voltage when you think about batteries. Because a lot of times when you have a battery, so like when you think of a battery, you generally think about it in terms of voltage. You know, like I have a 3-volt battery, I have a 6-volt battery. However, if you've ever hooked up a battery to a whole bunch of stuff at once, you'll quickly notice that there's only so much current it's going to put out. Like there is a limit to what your battery can power. And so the idea is your battery being a physical thing, while it might be a 6-volt battery, there's only so much current it will support. So it's really this combination of current and voltage that you need to think of when you need to think of is this battery suitable for my purposes? Okay. Okay, I think I'm good with these equations. Conceptually, is that sensible? Are we good there? Let's do a power homework problem then. There's actually 2 power homework problems. Let me do which one? Let me do number 20 because I like it the most. And we probably will have time to do another. Number 20. Number 20, because number 20 says you have a 600-watt toaster. And so if it takes 1 minute to make a piece of toast, how much energy goes into your toast? Toast. Okay. Just so you know, watt is a unit of power, so it's a joule energy per unit time, joule per second. And so if you know the power going into your toaster, that tells you your change in energy over change in time. And if you want energy, you can just take this equation and solve it for energy. You don't have to worry about the derivative in this case because we assume that the toaster is running at a constant 600 watts and that it isn't some weird curve spread out over time. So power times time. Okay, so I have 600 joules per second. What should I plug in for time here? 60 seconds, excellent. And I should come out with a pretty reasonable 36,000 joules. The next thing that we're going to ask is we're going to ask how much this is going to cost us. And I really should have looked up how much PG&E is charging for power these days, because I bet it's big. But just so you know, for this problem, it's saying, okay, if your power is 8.0 8.5 cents per kilowatt hour, how much does this cost? Okay. And I want to start with breaking down this kilowatt hour unit, because it's a weird unit, but it is actually what's standard for the US on your electric bill. Because so what they are charging you for is the amount of energy that you use, not the amount of current that's going into your house, not the amount of voltage that is applied across your sockets. It's how much energy leaves the grid and gets used. And so if you look at this thing, a kilowatt, so that's an energy per second, so that's joules per second. An hour, we can talk about that in terms of like seconds. You multiply those two things together and you're left with energy. And so while it's a very obscure way to get to joules, a kilowatt hour is an energy. It's not a power, and it's not a voltage or an amp. It's an amount of energy. Sound okay? Okay. Which is nice, because just because like you're running something at a high voltage doesn't mean that you should pay more. So if you have 8.5 cents per kilowatt hour, and so I might even write this down as, no, I'll write it down as a kilowatt hour. Kilowatts. I'll write it down as 10 to the third watt hour. And then you need to multiply this by 36,000 joules. I need one more conversion factor. So I have watts, which is joules per second. Joules per second. And I have hours, and I have joules on the top. What's the last conversion I need to make to get something in cents? Time, yeah, because I have seconds and hours, and that doesn't match up. But I could say, okay, 3,600 seconds is 1 hour, and then I'd be back in business there. Does that sound reasonable? Okay. So now I have 360 divided by 36, also divided by 1,000, multiplied by 8.5. Plug that into your calculators, or don't, and actually just do the conversion. 0.085 cents. So first off, pretty reasonable. Just, you know, PG&E, one of the numbers I have here is at least 22 cents per kilowatt hour. So this problem is a little bit out of date. Okay. That okay? Power good? Should we run another problem, or do you guys feel confident about this? You guys sound confident about this. Let's do number 17. I don't feel confident about this. Number 17 is good. So number 17, we have 2 electric bulbs. Bulb A and bulb B. The resistance of bulb A is twice as much as the resistance of bulb B. And imagine that these guys are in a circuit in such a way that the voltage across A is the same as the voltage across B. So like the voltage drop across both of these are the same. Which of these bulbs is going to be brighter? The one with the higher resistance or the one with the lower resistance? What do you think? Okay. Which one? The lower one? Are you saying B? Are you saying B? Let me ask you, if they have the same voltage across them, which one will have more current through them? So I got V equals IR. If they have the same voltage, which one will have more current? The one with the higher resistance or the lower resistance? Yeah, so lower resistance gives you higher current. And just so you know, more current means more brightness, because remember how I was talking about resistors take that current, and that's where they get the energy of how much kinetic energy can you put through them in terms via that current. And so more current means brighter. So A has twice as much resistance as B, so B is going to be brighter. Make sense? You can also run it through a power equation where power equals V squared over R. And so if they have the same voltage, the one with the lower resistance will be giving off more power in terms of lights. Now, okay, so now they were hooked up like this. Now I'm going to hook them up in series. Before they were hooked up in parallel, just so you know. Now I'm going to hook them up in series where I have bulb A and bulb B. So there's A and B. The thing with the resistance is the same. A still has twice the resistance of B. Are they still going to have the same voltage across them? No, right? No, because the one with the higher resistance will probably have a higher voltage drop. What about current? Could we say something about the current that goes through them? They should have the same current, because when they're in series, when they're one after the other, any charge that goes to the first one has to go through the second one, right? So now what we know is their currents are the same. Okay, if their currents are the same, now which one is brighter? Let's go to your power equations. IV, V squared over R, and I squared times R. What do you think? So you're saying the one with the highest resistance? All right. And you would be correct. Okay, and so let's talk about this a little bit, because I like the whole, well, they're the same brightness because they have the same current. That is a really good place to start. However, you might think about resistance, about how much energy a resistor can pull out of a current. So if you think about copper makes a terrible light bulb, right? It doesn't glow. However much current you put through it, it doesn't glow. To get something to glow, you have to find a slightly non-conductive, like thread, what will glow. Wax covered thread will glow. And so the resistance means that inside the light bulb filament, the electrons are smacking into each other and the thing that they're going through. And when they smack into those things, that gives off energy. And that energy turns into light. And so if you don't have anything to smack into, you're not going to get all the energy will stay with the electrons. But if you have something to smack into, then you can give off a whole lot of energy. And so basically bulb A, which has a lot of resistance, it's sucking a lot of energy out, versus bulb B, which is taking energy out, but just not as much. Generally okay? Okay, I am about to wrap up this chapter, guys. Are there any other problems that you guys want to look at before we wrap it up? I think we've done kind of one of each, so you should be able to get through the homework pretty well. Okay, then if you guys are good, you do have this homework due tomorrow, quiz over the weekend. Those of you in lab, I'll see you in a few minutes. And we'll start DC circuits next week. It'll be fun. I promise. Okay, bye everyone.